It's pretty wild when you think about it. What could a simple bouncing spring possibly have in common with a complex electrical circuit? I mean, on the surface, absolutely nothing, right? Well, it turns out they actually speak the exact same language, the language of math. Today, we're going to pull back the curtain on this amazing unseen connection and see how one powerful idea can describe two totally different parts of our world.
So let's start with the spring. Imagine you pull down on a weight. You let it go, and it starts bouncing up and down, up and down. How in the world could we predict exactly where that weight is going to be at any given moment? You might think it's just random, chaotic bouncing. But nope. There is a deep, beautiful order hidden inside that motion, and we're about to find it. Okay, now I know what you're thinking. That looks a little scary, but don't worry. Think of this equation less like a math problem and more like a story. It's a sentence that describes how the spring's acceleration, its velocity, and its position are all connected. It basically says, hey, if you tell me where the spring started, and you tell me what forces are acting on it, I can tell you its entire future. It's like a recipe for predicting motion.
All right, so our first job is to take this physical object we can all picture, that bouncing spring, and translate it into one of these powerful mathematical sentences. We're going to build our model step by step.
So, to build our model right, we first have to understand the forces at play. You've got the spring just hanging there, unstretched. Then, we attach a weight. Gravity pulls it down, and the spring pulls up, until they find a perfect balance, a sweet spot. We call that the equilibrium position. All that bouncing we see is really just the spring trying over and over again to get back to that one single point of balance.
Now, the secret sauce for how a spring behaves is this wonderfully simple rule called Hooke's Law. All it says is the more you stretch a spring, the harder it pulls back. It's that simple. And that little letter K there, that's the spring constant. You can think of it as the spring's personality. A really high K is a super stiff, tense spring. A low K is a loose, kind of floppy one. Building the actual equation is like following a super simple three-step recipe. First, we figure out the mass. Easy enough. Second, we use that to find the spring's unique K value, its personality. And third, we just plug those pieces into our equation. And boom, with just those two numbers, we have a complete mathematical model that can describe the spring's entire future.
But hold on a second. In the real world, a spring doesn't just bounce forever, does it? It eventually slows down and stops. That's because we're missing one more crucial ingredient. Another force that's always at play: damping. Damping is really just a fancy word for things like friction and air resistance. You can think of it as the universe's brake pedal. It's always pushing against the direction of motion, slowly and surely draining the energy out of the system until everything just comes to a stop. It's what makes our models realistic.
And this is where it gets really cool. Now, don't get bogged down by the specific equations here on the left. The big idea, the key takeaway, is that by changing just one number, the amount of damping, we get three completely different kinds of motion. You can see them in the graphs on the right. We call them overdamped, critically damped, and underdamped. Let's see what those actually look like.
And you've seen these concepts everywhere in your life. An overdamped system, that's like the closer on a screen door that shuts nice and slow and smooth, no slamming. Critically damped motion is the dream for a car suspension. It hits a bump, absorbs it, and gets right back to normal instantly, no extra bouncing. And underdamped is our classic example, the bouncing spring, or maybe a guitar string that vibrates back and forth before it finally fades out.
Okay, so we've built this really complete model of our spring. We get it. But what if I told you that this entire mathematical story that we just wrote has an identical twin, a kind of ghost, living in a completely different part of physics? Okay, let's totally switch gears. We're stepping into the world of electronics now, and we're going to look at something that seems totally unrelated, an LRC circuit. It's got three main parts: an inductor, L, which kind of hates changes in current, a resistor, R, which is like friction for electrons, and a capacitor, C, which stores up and then releases electrical energy.
All right, get ready for the big reveal. On the left, you see the equation for our spring with its damping. On the right, the equation for our LRC circuit. Now, just look at them. Forget the letters for a second. Just look at the structure. They both have a second derivative term, a first derivative term, and a plain old variable term. They are mathematically identical.
And this is not a coincidence. This is a deep one-to-one analogy. The inductor, L, resists change in current. Just like mass, m, resists a change in motion. The resistor, R, creates electrical friction, just like our damping, beta. And the capacitor, well, it stores and releases energy exactly like the spring constant, K, does. One system is moving a weight through space, the other is moving charge through a wire, but the rules they're following are exactly the same.
So just let that sink in for a moment. The elegant little dance of a bouncing weight and the invisible flow of electricity in a circuit. From a mathematical point of view, they are the exact same thing. They're just two different ways of seeing the same fundamental pattern of the universe.
So you might be thinking, okay, that's a neat party trick, but why does this really matter? Well, the importance of this discovery goes way, way beyond just springs and circuits. It tells us something really profound about how the universe is put together. It gets at this incredible idea that the physicist Eugene Wigner famously called the unreasonable effectiveness of mathematics. Isn't it just bizarre, even a little magical, that these abstract patterns that we dream up in our minds can so perfectly describe how the physical world actually works? This whole spring-circuit connection is a perfect, beautiful example of that mystery.
And this model isn't just in springs and circuits. I mean, it is everywhere. The same fundamental equation is used by engineers designing skyscrapers to withstand wind, by biologists modeling how predator and prey populations rise and fall, and even by economists trying to understand the boom and bust cycles of the market. Any system that swings back and forth around some stable point is singing this exact same mathematical song.
And that leaves us with a final, kind of mind-bending thought. If a spring and a circuit are secretly twins, what other, even deeper connections are still hiding out there in plain sight, just waiting for us to find the right mathematical language to reveal them? The world is absolutely full of these hidden patterns, and now you know how to start looking for them.